Alright everyone, welcome back. This is going to be the first chapter of electricity, which is going to be magnetism, guys. So looking at this first question here, in which pair are both magnetic materials? Obviously it is going to be iron and steel, right? Like I mentioned in class before, iron is considered a soft metal and steel is considered a hard metal. Both of them are going to be magnetic. Aluminium is not ferrous, copper is not ferrous as well, and aluminium is not ferrous, so these are definitely not the answers. Then looking at question number 2 here, which method could be used to demagnetize a magnet here? Place it in the east-west direction and hammer it. This is possible. Place it in the east-west direction and heat it until it's red hot. This is possible. Pull it slowly from a coil carrying an alternating current. This is possible as well. And put it slowly into a coil that's carrying a direct current. This is absolutely impossible. So the answer can be no other than A. And question number 3, a strong electromagnet is used to attract pins. What happens when the current in the coil is half? When you halve the current in the coil, you're going to halve the magnetic strength. So obviously less pins will be attracted, right? Some pins are attracted, but not as many. This is not true. Same number of pins attracted, not true as well. Then more pins are attracted, not true for sure, right? In 2 separate experiments, a magnet is brought near an unmagnetized iron bar. This causes the bar to become magnetized. So this is magnetic induction here. If this is the S, this will be the north, then this will be the S. If this is the north, this will be the south, and this will be the north here. So which magnetic pole is in use at X and Y? Always remember, guys, as soon as you have a magnet touching an iron bar, the immediate opposite becomes the opposite pole. So if they're asking for X, which is obviously going to be north, Y, which is also north here. That's why the answer is going to be A in this question here. Then moving on to the next part. A student suggests 3 methods to demagnetize a piece of steel. Placing it in the east-west direction and hammering it possible. Placing it in east-west direction, hitting it red hot, removing it is essentially the exact same question just now, right? So donkey is definitely the answer here. Then looking at the final part in this year here, figure 8.1 shows a coil wound around a steel bar that is initially unmagnetized. Any appropriate power supply can be connected between the terminals A, B here. So when they say appropriate power supplies, they mean that it could either be an AC or a DC. No other apparatus are available. Then after that, they ask you to describe how the steel bar can be magnetized. Obviously, first and foremost, if you want to magnetize a steel bar, you have to use a high DC current that allows the current to flow in this coil here, which will eventually magnetize the steel bar, right? So first and foremost, you're going to say like connect AB with a DC power supply and run high amounts of current in the coil, or the solenoid in the coil, right? Then after that, to demagnetize it is the exact opposite. Connect AB with a AC power supply and slowly remove the steel bar from the coils before turning off the current. This is quite a standard answer, guys. In your IGCSEs, always remember that there are mainly 3 methods to demagnetize: either hammer it, or heat it, or either remove it slowly from an AC power supply. Alright, then moving on to the next part here. A small compass is placed close to a strong bar magnet the same distance from each end, which diagram shows the direction in which the compass needle points. Now you have to understand that this compass here is actually a weak magnet, whereas this one here is already mentioned to be a strong magnet, right? Strong magnets will always influence the direction of the weak magnets, meaning to say if the magnetic field looks something like this, right, the compass should be pointing in the downwards direction as well. So this is not possible, this is not possible. This one here, you'll see that the magnetic field is like this, right, and the compass is pointing downwards. That's why C is going to be the answer here. Alright, After that, a bar magnet can be demagnetized by hammering it for a long time and slowly removing it from a power supply. Which row completes the description on how these processes are carried out? Hammering the steel bar, the magnet should be aligned to the east and west direction, right? And then slowly removing it from a steel bar, from a coil, is obviously the AC power supply. So B is definitely the answer here. Then after that, a child's toy, metal fish are lifted out of the toy pond using a metal rod. These fish are magnetically attached to the end of the rod. There is no magnetic forces between the fishes itself. So obviously this is the magnet and these are just the iron, right? What are the possible materials from which the fish and rod are made of? The fish should be made of something ferrous, so aluminium is definitely out of the question. The rod should be made of a permanent magnet, so steel bar is the only answer here, guys. Permanent magnets always use steel bar. Electromagnets use irons. Right. Then moving on to the next part here. What are the most effective methods of demagnetizing a bar here? Demagnetizing a bar could be either hammer, heat, or AC power supply. Placing the magnet in a solenoid carrying a large alternating current and gradually decreasing the current. This is obviously the answer. Placing a large direct current, not possible. You should be alternating current. Placing the magnet that produces a magnetic field in the opposite. This is not possible as well. Placing the magnet next to the identical bar that is posed. Yeah, not possible. Different polarities are not going to demagnetize. So looking at the next part, a magnet near a coil of wire is attracted to the coil when there is a current in the coil. Which statement explains these forces of attraction? The current in the coil is actually going to produce magnetic fields in the coil, right? So the coil of wire have its own gravitational field, illogical. The coil of wire is made of soft iron. This is possible, that doesn't really explain the attraction. The current in the coil creates a magnetic field, more logical. The current in the coil wire induces a charge. Answer is definitely going to be C here. Okay. Then after that, a student demagnetizes a magnetized steel bar. He places the bar in a solenoid connected to a power supply. He then removes the bar of the solenoid. Obviously the power supply here is supposed to be AC, so this is impossible. Speed removing the bar should be slower, so answer should be B here, guys. Alright, then what is wrong with this labeled diagram of a permanent magnet? If it is a permanent magnet, it should not be made of iron, it should be made of steel, because iron are for electromagnets, whereas steel are for permanent magnets here. So the cross section should be rectangular, the length should be blah, blah, blah. The magnet should be made of steel. Obviously, this is the answer here. Alright, then moving on to 8 and 9, 10, 11. In which way are bar magnets and an electromagnet similar? A bar magnet and electromagnet always magnetize when stored, not logical. A bar magnet and electromagnet can both be used to separate magnetic and non-magnetic materials. Yes, definitely. Guys, I've mentioned this in class before. Always remember that only magnets can separate magnets, because only magnets can repel each other, right? Magnet repel each other. If it's magnet and metal, they will always attract. A train of steel nails and a train of iron nails hang from a strong magnet. These trains are carefully removed from the magnet. What happens? So basically this is a strong magnet. Some are made of steel, some are made of iron here. This concept here is basically trying to test your understanding that steel retains its magnetism, so will still be attracted, whereas iron is a soft metal, easy to demagnetize, so it should fall off here. Both trains fall off. Not true. Both trains stay together. Not true. Only the trains of iron fall apart. May be possible. Only the trains of the steel fall apart. Not possible. C is the definite answer here, because the irons will fall off and the steel nails will still attract each other because they retain some of its magnetism. How can a permanent magnet be demagnetized here? Same thing. Cool the magnet. Not possible. Place it. Not possible. Pull it out of a coil connected to an AC power supply. The only logical answer here. And finally, question 11, an old expensive steel watch becomes magnetized. The owner wants to use the watch again. He must demagnetize the steel watch. What is the best method to do this? Insert the watch in a solenoid that carries alternating current and then slowly removing it, possible. Insert the watch in a solenoid carrying a direct current, not possible. Pass alternating current through the watch. I don't think this is advisable. Of course, you're going to mess up the circuitry, right? Pass direct current through the watch, definitely not possible. So A is the only logical answer here. A bar magnet is made of made of metal. Suggest a metal from which the bar magnet is made of. Definitely it should be steel because like I keep saying, steel is considered a hard metal. It is hard to magnetize and hard to demagnetize. Describe a method for demagnetizing a bar magnet. Here there are many methods. Either you hammer it in the east-west direction, you heat it in the east-west direction, or remove it slowly from a alternating current, right? But I'll just write hammer the bar magnet in the east-west direction. Repeat repetitively. Okay. Then finally, the figures 10.1 shows a wire that carries a current in the page. Current going into the page represented by X. The circle on figure 10.1 shows the pattern of the magnetic field around the wire. On figure 10.1, draw an arrow on each circle to show the direction of the magnetic field. Obviously here, if the current is carrying, if the wire is carrying the current and is going into the paper, you're supposed to use the right hand grip rule, which states that this here is the direction of the current and your four fingers are the direction of the magnetic field, right? Using the right hand grip rule, point your thumb into the finger and you'll notice that your four fingers are somewhat in the clockwise direction. So you just need to draw these arrows here and you're good to go. Then after that, state why the spacing of the circle increases as the distance from the wire increases. The reason so is because this is to indicate that the further away it is from the source, which is the current here, the weaker the magnetic field is. So you're supposed to mention that as the magnetic field gets further away from the current, it becomes weaker. Or you could even say that the magnetic field strength becomes weaker or decreases or so on. Anything that's logical. Okay? Then moving on to the final part here. An electromagnet is used to remove a splinter from an eye. Okay. What material is the splinter made of? Obviously something that is magnetic, not aluminium, not glass. Could be iron, definitely not wood. A steel magnet is placed inside a coil of wire. Which method is used to demagnetize the magnet here? Obviously it should be AC, so DC DC is definitely out of the question. And slowly remove it from the coil, so B is the definite answer here. A permanent magnet is placed close to a bar of soft iron. What are the polarities of P and Q? Like I keep saying, as soon as you place a permanent magnet onto these iron bars here, you're inducing it with magnetism and you'll have the immediate opposite with the opposite pole. So P is obviously S and Q is obviously N here. Which method is used to demagnetize a bar magnet? Lowering it in water, but heat it up with a Bunsen burner may be possible because you're heating it. Place it in a metal box, suspend it into a spring, not possible. Which method is used to demagnetize a bar? Yet again, cool it in the freezer, drop it in a beaker of water, place it in a coil carrying a direct current. No, it should be alternating current. Strike it with a hammer, possible. Alright, and the iron is used for a core of a transformer, and steel is used to make a bar magnet. Which statement explains why usage of iron and steel? Yet again, iron should be a temporary magnet, steel should be a permanent magnet. Iron is a magnetic material and steel is a non-magnetic material, not possible. Iron is a permanent magnet, not logical. Iron is a temporary magnet and steel is a permanent magnet, logical. So C is the definite answer here, right? Then moving on, a bar magnet is placed inside a current carrying coil. The diagram shows 4 different experiments. In which experiment is the magnet demagnetized? If you're demagnetizing it, it should be alternating current, which has this symbol here, right? These 2 are definitely out of the question, so it should be 1 and 3, guys. All right, you can either slowly remove the magnet or you can slowly reduce the current in the coil. Both is acceptable. Then, no, not finally. The diagram shows a bar magnet at rest on a smooth horizontal surface. The length of the soft iron wire is held parallel to the magnet here. The wire is released. What happens? Obviously the wire will be attracted to the magnet, right? The wire moves away from the magnet, moves towards the magnet. The wire center stays in the present. Not logical. And then what else? The wire center stays in the present position and rotates 90 degrees. Not logical as well. B lah, definitely right. Because it's not even pivoted lah, so it's going to be attracted inwards. Okay. Then final question, which diagram shows the pattern and the direction of the magnetic field line around the magnet? It should always go from north to south here, right? And it should never intersect each other. So looking at these answers here, whichever is not north to south is definitely out of the question already. And it's either between this or this, right? Which obviously C is the more logical answer here, because yeah, the magnetic field is going to curve around, right? Yeah. Actually, what an odd question. Actually, A and C are both okay, I guess. But if you were to choose between 2, I'll choose C as the answer. Okay. Then, next. Figure 9.1 shows a permanent bar magnet to a circuit that contains a coil and a galvanometer. Suggests a metal from which the magnet is made of. It's obviously supposed to be steel, because steel are used for permanent magnets here. Alright, and that concludes the 3 exercises.